life comes in many different forms, from tiny to big. And these earthly forms of life exist in a variety of places, from ice masses in Antarctica, to deserts, to steaming jungles of Africa, from the air to the cold sea, and even in springs of boiling water. Some life forms swim, some walk, some crawl, some fly. Life is indeed diverse. On Earth, there are thousands of different life forms which have adapted to the unique environments. It seems that on Earth, man stands as the most intelligent life form. But what about the universe? Are we alone? Or are there other life forms similar to or possibly different than those on Earth scattered about the far reaches of space? Where might other intelligent life forms reside? I'm Lynn Bondurant at the NASA Lewis Research Center in Cleveland, Ohio, and I'm your host for a series of 13 programs about life in the universe. We'll see how man has learned to live in space beyond the protective atmosphere of Earth. We'll also see how man is looking for extraterrestrial life. When man first ventured into space, to orbit Earth from periods of hours to as long as months, he was able to carry enough food and water to sustain him. But as we plan ahead for even longer space trips, we must find a way to grow food and reuse air and water. In the next few minutes, we'll see film segments which explains how we can solve these problems. The films were produced by the National Aeronautics and Space Administration during the early 60s.
It was inevitable that man, the insatiable explorer, would one day build a stairway to the stars and venture into that harsh and unforgiving void where nothing is friendly or favorable to his biological system. In these early flights, man demonstrated he can blast himself into the near reaches of space, survive the uncompromising vacuum, the strange state of weightlessness, and then plummet back through Earth's blanket of air safely. In space, man must assume many roles, that of pilot, navigator, equipment operator, scientist, decision maker, medical man, and other roles as required. It is impossible to build a machine that can remotely match his brain, his spirit, and power to reason. If we could, it would greatly simplify space exploration. So, man himself must venture into space. Today, we can send him there with enough water, oxygen, and food to sustain him for a week or two. Now, men of vision are adjusting their sights on the future, when we may want to send several men into space, equipped for missions lasting many months or years. Living in space for these longer periods of time means a large supply of oxygen, water, and food. We must surround man with an environment acceptable to his physical, psychological, and social makeup. An awesome task added to the already complex problems of space exploration. Before we can realize these goals, though, there is much to be done by this generation and those who will follow. We are now in the process of developing a life support technology. When the day comes to launch men on extended space missions, we will have the know-how and the equipment capable of sustaining them in safety and good health. Considering first just the basic necessities of life, We must create an encapsulated, self-sufficient community with its own pressurized atmosphere, water system, and food supply. It must carry its own Department of Sanitation, recreation center, communication system, and above all, a place to work. All of these needs occupy space and add up to a lot of weight. More weight than we can lift into space if we are to take all the oxygen, water, and food needed for long journeys. To reduce the amount of stored supplies carried, we need a regenerative life support system, machines which can convert waste products back into a usable form. The ideal regenerative system would be one in which an initially small amount of water, oxygen, and food aboard the spacecraft could be used over and over again, indefinitely. Machines which will do this require a great amount of energy. Energy, then, in the form of electricity or heat, is the key, and one of the more complicated problems. Energy doesn't weigh anything. But the machines that produce and control it do. For a regenerative system to be practical, the weight and volume of the power generator, plus the regeneration equipment for life support, must be considerably less than the stored supplies of water, air, and food we are trying to eliminate. Of all consumables, earthbound man uses more water than any other. On Earth, water is plentiful, so he uses a lot of it. But in space, he'll only have the water he can take along with him. Here, he will be required to get along with considerably less than that to which he is accustomed. We will allow each man about 1.5 gallons of water per day for drinking, food preparation, and personal hygiene. Even on this reduced basis, 4 men, for example, will use approximately 2,000 gallons, or 16,000 pounds of water during a 1-year mission. By regeneration, the same water is used over and over, so we can reduce the total amount of water required for the entire mission to 17 gallons or 140 pounds, just enough to start the equipment working. Regeneration of wastewater begins in the collection tanks, one for humidity condensates, a second for used wash water, and a third for urine. Chemicals added to the stored wastewater inhibit bacteria growth and the formation of objectionable gases. From the storage tanks, water passes into 2 identical units which distill the used water. One unit distills wash water and humidity condensate. The crew uses this purified water for drinking and food preparation. The other unit distills urine, producing water which is more pure than that which we draw from home faucets. However, for psychological reasons, it is stored separately and used for washing. The wick evaporator is the heart of the distillation unit. It makes it possible to distill water in 0 gravity. Wastewater saturates the wick in an automatically controlled flow. Hot air then flows over the wick, evaporating the water, leaving most of the waste products in the wick. Charcoal beds filter out the remaining contaminants in the water vapor, which distillation did not remove. The water vapor then passes through a condenser and to a small centrifuge, which spins condensed water out of the airstream. A second charcoal bed filters the water as a final purification stage. The crew periodically tests the processed water for purity. In a year, the 4-man crew will consume 2,700 pounds of oxygen and exhale 3,300 pounds of carbon dioxide. The regeneration of oxygen from carbon dioxide achieves two objectives. First, it removes the poisonous carbon dioxide from the cabin air. Second, it separates the oxygen from the carbon atoms and restores the oxygen to the cabin air. The crew then rebreathes the same oxygen atoms in a continuous cycle. By removing the carbon from carbon dioxide, we have a source of life-giving reusable oxygen. The processing of air and the regulation of pressure within a spacecraft are the functions of the atmospheric control system. Oxygen recovery, one of the functions of this system, is accomplished with three units: CO2 recovery and concentration, CO2 reduction, and water electrolysis. The first of these separates the CO2 from the cabin air. In this unit, cabin air first passes through a silica gel canister. This dries the air. The dry air then passes through a canister of specially prepared zeolite, which captures CO2 only. Zeolite holds CO2 somewhat loosely. At about 1/2 hour intervals, airflow is diverted. Heat and a vacuum pump extract the CO2 from the zeolite. The pump delivers it to an accumulator. From here, it passes to the CO2 reduction unit. Hydrogen is introduced, and the unit mixes the two gases. Electric heaters raise the temperature of the gas mixture to around 1200 degrees Fahrenheit. As the hot mixture passes over an iron catalyst, the CO2 molecule reacts with the hydrogen. Oxygen atoms transfer to hydrogen, forming water vapor. Carbon adheres to the iron plate. Scrapers remove it in a continuous process. Filters trap the carbon particles for disposal, but allow the water vapor to pass through to a condenser, which converts the water vapor into droplets. A liquid gas separator collects the water, which moves on to the next unit. This unit has 3 identical electrolysis modules. Each module contains 16 electrolysis cells. These cells are specially designed to operate in zero gravity, where liquids and gases are difficult to separate. Water enters the cell and mixes with an electrolyte. It separates into hydrogen and hydroxyl ions. An electrical potential is applied to platinum screen electrodes, which attract the ions through special membranes. At the electrodes, the ions are converted to oxygen and hydrogen gases, while the membranes hold back the liquid electrolyte. The hydrogen gas obtained by water electrolysis returns to the CO2 reduction unit to produce more water. The oxygen returns to the cabin. Thus, carbon dioxide, exhaled by the crew, is continuously processed to recover oxygen for the crew to breathe again and again. If there were no losses, the air in the cabin at launch would sustain the crew indefinitely. However, some air will be lost by leakage through the cabin wall, and each time the airlock is opened. So extra oxygen and nitrogen will be stored to make up for these losses. The regeneration of food from biological wastes is far more complex, and today we don't know of any practical way of doing it. So we must take all the food needed for the mission, or devise a means of resupply at various intervals. Today, researchers are working toward development of life support systems capable of reclaiming foods from biological wastes. These foods of the future will not be on the menu of today's generation of astronauts. Even though we do not regenerate food from waste products at the present time, we save weight and space aboard the spacecraft by packaging freeze-dried food in zero-G-type plastic bags. The dried food is reconstituted by simply adding water. The menus are varied, tasty, and nutritional. Food occupies third place in survival time, but first place in satisfying a deep psychological need. Food management is not a regenerative system. The launch weight of food supplies is reduced by freeze-drying and pre-packaging main courses of the carefully planned menu. Astronauts prepare their meals by adding hot or cold water to the dried foods from a zero-G dispenser. Zero-G trays hold everything in place. Force feeding is the answer to weightless dining. Some of the solid foods are eaten, package and all. Thus, we have determined in this early development stage that it is feasible to construct a nearly closed regenerative life support system. However, there is a great deal more to manned spaceflight than supplying water, oxygen, and food. These systems are a distillation of our most advanced scientific thought, translated into functioning hardware, the beginning of a basic life support technology. Components in this system may or may not develop into flight hardware designs. This will depend on how well they prove out in long-duration manned ground tests. The design of an actual spacecraft must be tailored to a specific mission. We have to know what the mission will be, the size of the crew, their destination, and the duration of the total operation. These and many other factors will affect the spacecraft size, weight, and the amount of power required. Even though the types of missions will vary greatly, there are conditions and constraints that are common to all manned operations. The weight we can lift into space is severely limited. So the life support system must be as small, lightweight, and reliable as we can make it. We must also consider that everything, including man, must function in zero gravity. Weightlessness adds many design problems we have never faced before. The problem is complicated by the fact that it is extremely difficult to produce a truly weightless environment on Earth. Parabolic flights in a jet aircraft provide less than a minute of test time per maneuver. Research scientists have been able to extend test times by developing an underwater technique that in some respects simulates weightlessness. Another device, the free space simulator, approximates the difficulties encountered in doing useful work in zero gravity. In space, it will be virtually impossible to apply a twisting, pushing, or pulling force without something to hang on to. Our spacecraft designs must reflect an understanding of these problems and provide for them. Every system in a spacecraft, including man, either uses or produces heat, but more heat is generated than is used. The excess heat must be radiated to space. The amount to be radiated is constantly changing. Heat given off by the human body varies with the activity of the individual. Heat generated by electronic and process equipment fluctuates with the demands placed upon them. A spacecraft in Earth orbit may pass in and out of sunlight and Earth shadow many times a day, exposing the cabin to constantly changing temperature extremes. A thermal control system must sense this varying rate of heat generation and adjust the flow of air and fluids to ensure a regulated temperature. For example, air in a spacecraft is more than a source of oxygen for the crew. It circulates in, around, and through men and machines, picking up heat generated in the cabin. In a continuous flow, it delivers the air to machines and devices which clean, purify, and cool it. One of these is the air conditioner. The fluid which circulates through this unit is first chilled in the space radiator. It then circulates to various components in the spacecraft, picking up heat as it goes. Chilling water for beverages, condensing water in numerous processes, cooling and dehumidifying the cabin air, cooling equipment, and finally, giving up its load of heat to space. In a spacecraft, we will be able to provide only a limited amount of electricity. Consequently, we must design each component to operate on a minimum of electrical power. In generating electricity, there will be a significant amount of waste heat at a temperature too low to produce electrical power efficiently. But it is hot enough to evaporate wastewater and to provide heat to many other life support processes. In this way, waste heat becomes useful heat that would otherwise have to be provided by electricity. In order to regulate the operation of all systems in a spacecraft, we must provide a reliable system of instruments and controls. Many of the controls will be automatic. Others will require manual operation. Status lights will indicate the general operating conditions of all systems. This will minimize the amount of attention the crew must devote to monitoring and control. In instances where fluctuations of a temperature, pressure, or process event are critical, a warning signal directs the attention of the crew to the trouble spot before it becomes a serious threat to their safety. Crew safety is all important. The success of a mission is dependent not only on the crew being safe, but feeling safe. Safety must be built into the life support system. Critical components will have backup units that can be switched into the line if needed. For example, in this prototype, the water recovery system has 2 distillation units. If one fails, the other can maintain the normal supply of drinking water and half of the wash water allotment. If both distillation units fail, an emergency unit using special filtration techniques will purify exhaled water vapor and perspiration condensed from the cabin air. Under these conditions, the crew will use water for drinking and food preparation only. Also, there will be an additional emergency supply of water. The oxygen recovery system has 2 reactors in case one fails. If both reactors fail, the poisonous carbon dioxide would be discharged overboard. The crew would then draw oxygen from an emergency supply while making repairs. In the case of serious atmospheric contamination or loss of pressure within the spacecraft, crewmen will get into their pressure suits and connect directly with the spacecraft's atmospheric control system. The suits are also equipped with their own cooling system, pressure, and oxygen supply, allowing the crew to work independently of the spacecraft life support system. Sustaining man in space for long periods of time presents enormous challenges to present-day technology. Tomorrow, men will be living in space for long periods of time, observing, experimenting, recording, accumulating knowledge. Man will then be a true space explorer, the master of his new environment.
In the past films, we've been introduced to a process called regeneration, which is a fancy name for reusing water, air, and bio-waste during space travel. After all, that is the same process which is used on spaceship Earth to recycle our air, water, and food. So you see that even in the early 60s, we knew about the fundamentals of regenerative systems for spaceships. However, man faced many other obstacles which had to be surmounted before he could successfully undertake long space journeys. Some of the problems with which we had to deal are weightlessness and its effects on the body, radiation, and the vacuum of space, to name a few. During this series, we will explore the question of life and its possible origins. We will see how man has studied the human body during spaceflight to monitor how the human machine reacts to that harsh environment. Spacesuit design and use will be seen. We'll see how moon dust and rocks were carried back to Earth to be studied for evidence of life on the moon. We'll be introduced to instruments which were sent to fly by or land on planets in our solar system. We'll learn about the structure of the universe, black holes, galaxies, and stardust, and how they all relate to possible life, and maybe even extraterrestrial intelligent life in the universe. During the next program, Between the Atom and the Star, we will examine the NASA biosatellite. The biosatellite was the first successful U.S. satellite used exclusively to study samples of Earth life forms in orbital weightlessness. Until next time, this is Lynn Bondurant saying goodbye from the NASA Lewis Research Center in Cleveland, Ohio.